Okay, so we're just going to do some more linear regression stuff today. I just think seeing more examples is probably going to be the way to get better at this. So the Fifth Connect and Excel are up now. It should be a little bit shorter and easier than some of the other assignments. So they're due by the end of the week, so next Friday. We've really covered everything that you would need to kind of go through the entire thing, but just seeing more linear regression examples will probably continue to help with those. I think the Connect assignment's only 8 questions, so it's not quite as long as the other ones. I also put up some practice materials to start looking over for the final. It won't be comprehensive. I usually do a comprehensive exam, but just kind of the way that the semester is ending and how we cover material. I think we'll focus on what we've done since that last exam. So it'll be kind of all new stuff, and that should take us kind of to the end of the semester. Like I said, next week I'll be going over those practice kind of exams that I posted. We'll work through some of the problems, and if you have questions on specific ones and you sign on, I'll just keep on doing these review sessions at the same time we would usually have class. But we're doing that next week. Any questions for me before we kind of jump into things here? Let's see if I can pull the chat open here. He wants to be in the shot. So let's go here. So one thing that we will use today that I put up on Canvas, I will be going over this paper here. So MML and fatalities. So we'll start with some slides, but then we'll kind of jump to that paper. So just kind of reviewing some stuff with a different type of example. And I'll go through a couple different regressions, and then hopefully, like by the time we get to the end, we'll kind of see we have this complete picture of, I think, a fairly interesting question, right? So, universities have large athletic programs, specifically football and basketball. And we can think about, those universities want success, potentially in those sports because it can generate a lot of revenue, right? If we talk about things like, the whole reason why they didn't cancel kind of football season is because they still want to make a bunch of money with, having the games on TV, even if they can't get ticket revenue, right? So I had kind of this interesting idea, and kind of other people have kind of looked at it as well, which is, how can a school or a university influence whether or not they kind of have this athletic success, right? And specifically, we're going to look at kind of NCAA basketball, right? So I'm going to run the following regression where my Y variable is a 1-0 variable where it's a 1 if the team made it into that first round of the NCAA tournament. So their name would appear on kind of all those brackets, and it's a 0 if not. Right? So on the right-hand side, my X variable is the amount of money that school was spending on their basketball program. So I call it kind of B-ball expenses here. So this is measured in dollars, and then this is just one of those 0-1 variables. 0 if they didn't make it to the tournament, 1 if they did. So the interpretation that we're going to have on this beta 1 would be for every 1 unit increase in my X variable here, 1 unit would be $1 more spent on the basketball program, would increase my predicted Y value by whatever beta 1 is. Well, if I have a Y variable that is 0 to 1, I can think about that predicted increase being an increase in the probability. Step 1, I'm trying to teach here, okay? So if that's the interpretation we have for beta 1, the effect of a $1 increase, okay, what would I expect maybe the sign and the size of that coefficient estimate to be? Well, I would think that if a school is spending more money on their program, potentially it makes it more likely that they are going to have success or more likely that they'd make it into this tournament. Now, we haven't included a lot of other important variables, so we've talked about other examples in a couple previous classes where, even though we might expect this sign to be positive, if we leave out a lot of other important variables, we may be capturing not just the effect of a $1 increase on my basketball program, but other things that are correlated with both my X and Y variable. Right? But we would think it's probably positive, and I would probably expect that the size of the effect, the magnitude, probably pretty small. So why would I think that it's pretty small? Well, remember, it's a 1 unit increase here, and it's measured in dollars. So a $1 increase probably isn't going to have much of an effect. Right? However, if we want to do something like, well, what's the effect of $1 million? Right? Well, if I know the effect of $1 is this beta 1 hat, well, if that's the effect of $1, the effect of $1 million, I would just multiply that by $1 million. Right? So we talked about, I kind of already mentioned, if we have this limited variable bias, potentially, right, our estimate, and I think we went over this last class, but potentially our estimate here contains the true relationship between my y and my x1 variable. But this important variable I left out, x2, right, if I leave it out, I'm going to pick up some of the effect of that variable I left out in my estimate for the relationship between x1 and y. So I'll get the true relationship between x1 and y, but also this bias, right, this additional component. Right? So how can I eliminate this bias? Well, if I have data on this second variable, I can just include it as an additional control. Okay? So if we think about, maybe one important thing that we've left out is, well, schools that are larger in size have a higher number of undergraduates are going to have a higher number, higher amount of resources to be able to devote more money to maybe an athletic program. So we aren't accounting for the different size, the differences in the size of these universities. Right? So I could think about, instead of just running that simple linear regression, running a multiple regression here, where I've got multiple x variables. Right? So now now the interpretation of B1 is a $1 increase in basketball expenses would change the predicted y value by whatever beta 1 is, holding constant everything else I've included in this regression, so holding constant the number of undergraduates. So now the thought experiment is 2 schools with the same total number of undergraduates, one of them spends $1 more on the basketball program. Now, now beta 1 is the increase in kind of that y variable, but kind of holding that other variable constant, right? So we could kind of go through, I'm not going to put this on the exam or anything, but in terms of being able to put a sign to the bias. But if we know that the bias is this guy right here, so I've just kind of written that out, right? We'll pick up the true effect of the relationship between basketball expenses and whether or not they made the tournament. But we'll also have this additional component which would have whatever the relationship between the variable that if we would have left total undergraduates out, right? What relationship would we think it probably has with making it? Well, probably larger schools are probably more likely, so this beta 2 is probably positive. Variances here are always positive. And then the covariance, the relationship between x1 and the variable that I had previously left out, x2, well, probably larger schools probably are able to spend more money on their basketball program. So positive times a positive times a positive, our estimate before probably had this positive bias. I'm not going to expect you on any exam or even on homeworks to put a sign to that bias, but if we were going a little bit further in this class, those are the types of things that we could do. So we probably think that our estimate from running this simple linear regression was probably a little bit too high. We can kind of see if that's the case because I can run this regression as well. So here's some output, not from Excel, but from a program called Stata. We've got all the same things that just displayed a little bit differently. Notice here, instead of the intercept, it calls it the constant, same idea. Here's the coefficient on that x variable I included, which was basketball team expenses. You can see here it's very, very small, right? E to the -8, so that means move this decimal point 8 places to the left. Right? So it's pretty small, but that's because it's the effect of $1. We kind of already talked about that. How would I get my test statistic here? Simply divide my coefficient by the standard error. I'm told the p-value is 0 here, so I did find something that, estimated a coefficient that was something other than 0. Because remember, we start out always assuming that these slope coefficients are equal to 0. That was our null hypothesis all the time. So I can reject that null. I can say, I can reject that there's no relationship, or I found pretty significant evidence that there is a relationship, right? And that's because the p-value is 0. Look here at the r squared. We're, another word you might see, I think in the homework, it's referred to this a couple times in some of the problems that I assigned. But the R squared sometimes is called the coefficient of determination, right? And so it's saying how much are we able to explain of the variation in the Y variable using the X variables that we did. So basketball expenses here explain about 17% of whether or not a team will make it into the tournament or not. It's kind of how we can think about interpreting that. If I then run another regression where I include not just expenses, but also the total number of undergraduates the university had, I see that the coefficient did get a little bit smaller because we did have that kind of positive bias. Still very significant, right? P-value 0. And we could think about, we could start adding in additional kind of control variables here as well. But if we were to use this coefficient for right now, right? So that estimated coefficient, I moved the decimal point 8 places, pretty small. But the problem is, that's the effect of $1. I mean, on average here in the data set, schools were spending 1.3 million, right? And a standard deviation was 1.8 million. So you can think about even $1 million increase is a little bit more than half a standard deviation, right? So it's not unreasonable to think that some of these schools could spend another $500,000, right? So here we have the effect of $1. Let's think about for a school that's kind of in the top 100, a 10% increase in their budget would work out to be about $935,000. So if universities in that top 100 kind of for spending, if they increase their budget by 10%, spent another approximately $1,000, the effect would be the effect of $1 times $935,000, or about 0.069. So by spending almost additional $900,000, it increased their probability of making the tournament by 0.069, or a 6.9% more likely to make that tournament. And you could do this for different schools. So IU, a 10% increase in their budget would be 1.2 million. So right, if they increase their budget by 10%, they're going to get a slightly better kind of higher increase because 10% of their budget just works out to be a larger amount. Ball State, right, a 10% increase would only be 150,000. So even if they increase their budget by 10%, they only increase their odds of making the tournament by 0.011 or 1.1%. Okay. So I think that's, hopefully we kind of hit on a lot of things there, how we can take an estimate for one unit and get the effect of, say, 200 units, right? Or here, 935,000 units. We also kind of made sure we talked about kind of this p-value. If it's low enough, less than our alphas of 0.01, 0.05, and 0.1, we can reject that null, which the null is that we always start out assuming there's no relationship. Okay? And then we also kind of had a discussion about the R squared and some different interpretations. So this is interesting, but we can control for a lot of other things, right? So I could also think about, I want to control for the quality of the school in the year before. So I throw in kind of whether or not they made it to a tournament the prior year with their previous wins. Also, schools that are just generating more money from their basketball program are going to have more money to spend on it. So I'm going to control for revenues as well. I then kind of put in some dummies for years. This is just, a 1 if the year of that the data point I'm looking at was in 2000, a 0 if it's not. Another dummy where it's 1 if the observation was from 2001, 0 if it's not. And then kind of ran that regression here. So by including these additional controls, we're up to explaining about almost 30% of the variation in whether or not, a team made it to that first round or made it into the tournament. We can kind of see our estimated effect for expenses has gone down quite a bit. So I think it was like 7.3 something e to the negative 0.84. Now it's all the way down to 2.39. So a much smaller effect if we kind of control for everything else. And still pretty significant, right? P-value is 0.001, but that's still less than any alpha that we're looking at, right? 0.01, 0.05, 0.1. Okay. So this kind of just shows, it's always better, right? There's a lot of biases that exist when we go back to simply running a simple linear regression, like here. There's a huge bias in that estimate, right? Because we had a lot of other important variables that we were omitting. And, I didn't even really throw a ton of additional ones in here. And it alter that estimate quite a bit. So this kind of shows once again just the importance of, you know, making sure that if we've got information, we've got data, make sure we kind of control for as much other factors as we can. Any questions up to this point before I kind of, okay. So you can do the same thing for whether or not they can make the championship. I'm not going to waste a lot of time on this. You know, basically I'm just changing the Y variable here to be a 1 if they were the national champion, 0 if not. We get a really, really small effect. So, you know, you could say something like, you know, Ball State spent $150,000, remember, which is a 10% increase in their budget. It would only increase their chance of winning the national championship by 0.059%. So it's kind of interesting. But I want to move kind of now the discussion to where, okay, so these schools can pay, right? There was still a significant effect where they can increase their chances of making it into this huge national tournament by spending additional money on their program. And if they, you know, make it into that tournament, there's additional money to be made that the school kind of receives. So maybe they even, you know, if they make the tournament, they'll make their money back essentially. But outside of the athletic component, why, you know, a lot of people are don't have a favorable view of schools spending money on athletics because they say that's money that could go towards, you know, the other students, the other non-student athletes. The thing is, you know, well, what if there were some indirect effects of that success? So does basketball success, right, making it to this tournament, could it have positive effects in that school other than just in athletics, right? So one thing we could think about is, well, it's essentially, you know, there's, you know, millions upon millions of people who participate in this, you know, filling out brackets in March, right, for the NCAA tournament. There's tons of, you know, betting that goes on, but it's, you know, it's on the news, it's kind of a lot of different news sources online. So if you make it into that tournament, you're getting your name out there, potentially to people who might not have known your school existed before. So the example I always give with this is, you know, Valparaiso University, right? If I tell someone in California, you know, where, you know, do you know where Valparaiso University is? I'm guessing a lot of them might not know it's in Indiana, right? But, you know, or they might even know it exists at all. So, I mean, making it into the tournament, someone in California filling a bracket, seeing that university, seeing them play, hearing more about their story, I mean, they might consider, if not for themselves, but maybe, you know, their kids, maybe this is a potential school, right? They're talking about how good the academics are, you know, whatever the you know, the example is. So potentially this is kind of a like free ads once I make it into the tournament. I mean, I had to spend money to get there, but it's kind of getting my name out there. So following success, following making this NCAA tournament, do schools see an increase in the number of applications the following year? Right? So went out and grabbed some data on the number of applications that schools receive, and then whether or not that university's team made the tournament in the previous year, right? Because, you know, making it to the tournament in the current year, looking at, well, a lot of those applications, you know, happened before the tournament. So we're kind of looking back 1 year. So here, right, previous tournament is just a 1 if they made the tournament, 0 if not. Applications is the units here is like the number of applications, right? So a 1 unit increase, if we have an X variable that's binary, will be going from 0 to 1. So a university that didn't make the tournament, if they had made the tournament in the previous year, their applications the following year would go up by 7,000. You know, this seems like an outrageous effect, right? I mean, making this a tournament increases the number of applications you get by 7,000. Well, we haven't controlled for anything here, right? So whether or not they made the tournament, we already kind of looked at, you know, that athletic success is dependent on things like the number of undergraduates, how much money they're spending. And so, you know, we want to control for other things. But one thing that is really helpful is if we have information on the same variable from previous years, well, if I use the previous applications as a control, that will capture a lot of these other characteristics that are driving applications about this university. So I think I said that out of order. It's gonna be capturing a lot of the characteristics about that university that are kind of driving applications. Okay? So once I include the previous applications of the school, now it looks like making the tournament only increases my applications by about 100. Right? And the effect isn't quite significant, right? 0.13. If we're thinking about this is not less than an alpha of 0.1, so we at the 90% confidence level, we would fail to reject the null. And the null is that the relationship between previously making the tournament and the number of applications, that we start out assuming that's equal to 0, so we can't reject that. Right? However, I know that maybe other things matter as well. So I also simply kind of a little thing we could do here is include identifiers for, well, what state was the university in, right? If we look at California schools compared to Rhode Island schools, they're going to be very different in terms of the applications that they receive every year. Right? Even if everybody in the state becomes aware of this school that they didn't previously know about, Delaware, that's going to add a lot fewer than it would California. So if we look at kind of the results from that regression, first of all, R squared, we're accounting for 97% of the variation in our Y variable. And that's specifically because probably we have this previous applications in there, okay? So now we look at our previous tournament variable. If a university made the tournament the previous year, it increases applications by 167. And it's significant at what levels? Well, 0.017 is less than 0.1, so significant at the 10% level. Less than 0.05, so significant at the 95% level. Sorry, significant at the 5% level. And less than 0.0, oh wait, no, it's not less than 0.01, right? So we would not be able to reject it with 1% significance, but we could at the 5 and the 10% significance levels, or said differently, we could reject the null with 90 and 95% confidence, but not 99. So it looks like maybe there's some positive effects to the university outside of kind of athletics here. They get a higher number of applicants, right? They can admit more students, or even if they don't want to admit more students, they can be pickier with the students that they do admit, right? Maybe getting some higher quality students than they were before. So I'm then going to run the same regression, but look at, well, what if we replace this Y variable with some measure of incoming freshman quality, right? It's not a perfect measure, but I'm going to use kind of the freshman in classes ACT. I didn't use the average here. I kind of used the 75th percentile, right? So what was the 75th percentile of the incoming freshman classes ACT score? So that'll be some measure of like the intellectual kind of ability of the students that I'm admitting, right? So I run this regression. R squared is about 28%. So I'm only explaining 28% of the variation in the freshman classes ACT score. But I can still nonetheless interpret these X variables. So I look at previous tournament, right? So if they made the tournament the year before, it predicts that the freshman classes ACT, right, that 75th percentile cutoff goes up by 1.5, which seems pretty good increase, right? The ACT, I think I have it here on the next slide. It ranges, was it 17 to, yeah, if I look at the 75th percentiles at universities, it's between the range was 17 and 34. So going up by 1.5 is a decent effect. The p-value is 0, so we can definitely say that it's significant. We can reject the null hypothesis at every level. So sorry, here, the p-value is actually here. They're both 0, so it didn't matter which one I was pointing to, but the p-value is 0 here. Remember, if we wanted to calculate these test statistics, simply take the coefficient, divide it by my standard error. Okay. So how great is this effect? Well, the standard deviation was 3.5, so an increase of 1.5 is about a third to 1/2 of a standard deviation. So I think that's kind of I don't know, I thought that was interesting to kind of tie the whole thing together where, university starts out with this question, should we be spending more money on the basketball program? Well, it looks like we can improve success, be more likely to make it into this tournament. That's free advertising. If we make it into that tournament, it looks like there's not just additional revenue, but there's also these positive effects that come from kind of getting our name out there, more applications, and we were able to kind of select a higher quality student. So, I think this is it was a pretty good comprehensive example thinking about how we could use linear regression to answer some, an interesting question. Okay. Any questions over anything we just kind of went through there? Let's see the chat. All right. Okay, so now I want to go through, where is it? Oh, here it is. This paper, right? So I think I had it labeled MML and fatalities, right? So I wanted to kind of show you an academic paper, something that was kind of peer reviewed and published that uses some of these, like, uses multiple regression to answer some, I think, a pretty interesting paper or question actually, which is how have medical marijuana laws impacted traffic fatalities? Right? So this is how I read papers. Well, I usually read the abstract. Where is the abstract? Right here. So it kind of tells you in general what they did. I kind of explain, the idea is that with medical marijuana laws, maybe people, if it substitutes, if marijuana is a substitute with alcohol, right, then potentially we would see a decrease in the number of fatalities because there'd be less drunk driving, traffic fatalities, sorry, specifically. However, if they're complements, right, people use them at the same time, well, now if medical marijuana is legalized, maybe I see that people are using both and I see an increase maybe even in traffic. So we don't really know, right, but we're gonna try to figure it out with some data and multiple regression. So we come down here, multiple linear regression. So the way I read papers is I scroll down until I see something that looks like a regression equation. Right? Now, this is probably a little bit further than what we're going to do in this class, but the general idea still applies, right? So they did this thing where they took the natural log, but like I said, we're not going to cover that, so don't worry about that. Just think about we've got traffic fatalities over here. So how are traffic fatalities impacted by whether or not medical marijuana is legalized? So this variable, right, is just a 1 if medical marijuana was legalized in that state in that year. Okay? So the data kind of is every state, and I forget how many years they have, but I think it's, well, it probably says up here in the data portion, or we'll go here. Traffic fatality data, looks like they had it from, I'm not gonna be able to find it specifically now that I want to. But I guess it doesn't matter. They had like 10 years of data, if I remember right. So you've got every single state, 10 years of data. Some states never had it legalized. Some states always had it legalized. Some didn't, and then transitioned, or then kind of switched over. So we're going to be able to tell what was kind of the effect of legalizing medical marijuana by looking at this beta 1. Right? So we come down here. Oh, and they do a similar regression here. I'll show you the results eventually, where they look at the effect of medical marijuana on kind of alcohol sales. So they'll have 2 kind of different Y variables once we look at the data. So scroll on here. Let's look at the tables that they put together for us. Okay, so I'm going to focus on. Well, it's a little bit easier for us to read, given what we do in this class. Okay, there we go. So we're all the way on to table 7. So page 39. So here we've got kind of each column represents a different regression. So in this first column, the way we would kind of read this is they didn't have any controls. Right? Each additional column, they started to add in more right-hand side, more X variables, more control variables, right? Kind of culminating with the most control variables in this final column. Right? So you can kind of see if we just did this linear regression and we didn't account for all these other things, it looks like the effect is pretty large. Right? So, once medical marijuana is legalized, it decreases traffic fatalities. And because they did that natural log thing, it actually, we interpret this as a percent. Right? So, we want to work out, the number of fatalities we would just kind of keep it, wouldn't take the natural log, but a little bit outside of our class, so we won't focus too much on the interpretation here, just kind of on the sign and the significance. Okay. So it looks like it has a pretty large negative impact on traffic fatalities. Once we control for everything, it kind of is, less than half its size, right? Falling from -0.24 to -0.09. Also, when you read these papers, right? So like when we looked at the output from Excel, it gave us the p-value. Well, here they're not presenting the p-value to you, like the actual number, but they're putting stars for which levels you could reject the null at, right? So we would kind of say, or what levels there would be statistically significant at. So here in the naive regression, we could say that we could reject the null at all levels, the 1, 5, and 10%, right? So 3 stars means I can reject it at all 3 levels. 1 star means I can only reject it at the 10% level, not the 5 or the 1. And then 2 stars would be I can reject at the 10 and the 5. And usually the table kind of tells you that, but that's how we were going to interpret this. Okay? So it looks like they're decreasing, these medical marijuana laws are decreasing traffic fatalities, right? Which if you're a policymaker, like this is probably, you're advocating for this, this looks like a good thing. Our R-squared is pretty high. We're explaining 97% of the variation that exists in traffic fatalities. Okay. We come down here. We can also see that, well, what if I run 3 other regressions? I have all the controls in, but now I'm going to look at my Y variable is the traffic fatalities that had no alcohol involved, traffic fatalities that had some, anything other than 0, and then traffic fatalities that had very high blood alcohol contents. So you can see here, my significance goes away, right? For traffic fatalities that did not involve alcohol, medical marijuana laws really didn't have any significant effect. I can't reject this at any of my conventional levels, that it's anything other than 0. Remember, we start out assuming that these coefficients are equal to 0. I can't reject that, and so it could be that there's no effect of medical marijuana on traffic fatalities with no alcohol involved. However, when alcohol is involved in a traffic fatality, those types of fatalities have, gone down quite, a decent amount. This is a kind of larger than the estimate I think we had in the previous slide or previous table. And we can reject that null, that the relationship is not equal to 0. We can reject that it's equal to 0. So we're saying it's not equal to 0 at that 10% level. So we got 1 star here. And similar, it also decreases traffic fatalities that have very high blood alcohol content. And we can say, we can reject the null there at the 10% level as well. Okay. So it looks like these medical marijuana laws are reducing traffic fatalities, specifically through the avenue of a reduction in kind of the use maybe of alcohol. Right? Scroll down to this next table. Another kind of indicator of this is kind of interesting. Notice we don't have any significance here, so it doesn't really have a significant effect on traffic fatalities on weekdays or during the day. And I forget the time cutoff they used here for day, but I imagine it was like sunset or something. But notice traffic fatalities on the weekend and traffic fatalities at night are the ones where you see kind of this reduction, and it's significant at this one's significant at the 10 and 5% level. This estimate is significant at the 90% level. So it looks like, maybe, it's not so much a complement with alcohol, but maybe a substitute. So the next thing we can do to understand that, and this is a further support. I won't spend too much time, but they also broke it down by age, where you see the greatest reductions are kind of in these younger age ranges. So can we actually say that it's, is it operating through a reduction in the use of alcohol? Well, if we look at sales, right, people kind of, they say, what people do with their money kind of tells you what they're doing. So if we look at beer sales here, when medical marijuana is legalized, beer sales in those states went down, right? And significant at every single level. Wine and liquor sales, no real effect, but beer sales, we can say definitely went down. So this is a pretty interesting paper, kind of showing the power of linear regression. Like I said, even some more of the power that I didn't even dive into because it's outside the scope of this class by using kind of like the natural log. Right? But really interesting paper. I think it's the only thing that was left kind of here. They did a thing too with some survey data and found that like the number of drinks people have kind of maybe goes down a little bit, but it's pretty sketchy. The results aren't very strong, not a lot of significance. So that was a pretty interesting example to talk through, and kind of, like I said, just trying to reiterate the same things as we're going through these examples. I want to do one quick thing. I had this data set that I always think is somewhat interesting. I think I presented some results to you earlier in the semester, but it also allows me to give you some troubleshooting when you're trying to use this linear regression tool in Excel. Okay, so I've got a pretty not very clean data set here in the sense that I have a lot of missing variables. So I can't. If I have a missing variable and I try to run a regression, well, I'll show you. So we go data analysis. Hopefully we've tried adding that in by now, and if we are having problems, reach out to me. So I'm going to say my y variable here is what's the total weight that these individuals lifted in this powerlifting meet, right? So this is a powerlifting meet data set. It's got the total amount that they lifted, right? So I select that. My x variables, maybe I think about, well, I want to know, does their body weight, how is that correlated with their body weight? So I'm going to select, notice with all these, a lot of a pain in the butt. So can't use my shortcut because there's all these missing values. So let me go here. I'm going to select my x variable, which was body weight. It's going to take me a while to scroll down, which is annoying, but I have these blanks. There's probably another way I could do this real quick, but I'm actually going to try to do this. Let's see. I got another idea. There we go. Except for now, I just want to select this variable. All right. I want to show you this error, but I don't want to waste too much time on selecting this. So I'll show you in just a second. So this isn't really perfect, but let's just do like, let's say we only had, I don't know, the first 28, 27 observations. So then let's use my x variable as body weight. Okay. If I try to run this regression, it's going to say lin-est error, right? So what that's saying is there's missing values, right? So one way we can clean data sets up is if I just go to the very first variable, select, so control shift, hit the over arrow and then the down arrow. I've selected every single observation. I'm going to filter, hit that, go to data and hit that filter button. So go to data, hit that filter button. Now when I go back up to the top, every variable has one of these little arrows, right? So what I can do is I can say, okay, here's all the values that are in this variable. I want to remove the blanks. Okay? So I'm going to go to the body weight one. I'm going to deselect everything, go down here to the blanks and say, I can't use these. So I just want to select these observations and I want to delete them. Right? Now, usually, on this one, I have my raw data on a different sheet. So you don't want to delete your original data. You want to copy and paste it over to another sheet before you start deleting things. I think I mentioned that last class. Hit OK here. Now, hopefully, in this total kilogram one, I don't have any blanks. Nope, no blanks. So now when I go to my data analysis, regression, my y variable, I'm going to select is this total kilograms lifted. Control shift or command shift on a Mac down arrow. My x variable, I'm going to take their individual's body weight, and I believe these are all in kilograms. If you're thinking, how do people weigh 62 pounds? I selected the labels, and I'll hit OK. Now everything's running OK. So for every kilogram heavier an individual is, they lifted 3.4 more kilograms total in these powerlifting meets. I thought the other thing that could be interesting, you could play around with this. And I didn't look at the results ahead of time, but you could kind of play around with adding in their age as a control, adding in kind of their gender, so making that a kind of a binary variable over here. 1 if they're male, 0 if not. We could even really control for kind of the year if we really wanted to. So this is a kind of a fun little data set. Probably play around with it a little bit more on Friday. I'm trying to keep these recordings this week a little bit shorter. So I'll upload a smaller version of this to Canvas because it's a pretty large file with having a lot of observations. I'm going to trim it down a little bit and post it before next class, and we'll do a couple little regressions with it on Friday. Okay. I'll also post another here we go. Another paper just kind of under files on Canvas that we'll probably look at next class, so we get a little bit of flavor of what it looks like when people take this linear regression and apply it to different questions, different problems. Okay. Any questions from me before we kind of end things here today? Like I said, I'll probably keep these a little bit shorter this week. Okay. All right, that fourth Excel and Connect assignment are due this Friday by the end of the day, and then that fifth Connect and Excel assignment are due next Friday, right? So if you have any questions with those, please let me know, and I'll kind of schedule a Zoom meeting, or you can try to assist you via email. Other than that, I will see you guys on Friday.